So the following lecture is about projectile motion, and those that have taken physics have had some exposure already, and those that will take physics coming up, you will also have some exposure to projectile motion. And essentially what we're doing is we're going to talk about the motion of an object once it becomes airborne and behaves and how it interacts with gravity to produce the motion in flight. And so essentially projectile motion describes the path of a body or an object in air. And there's truly two external forces that will behave on an object when it's in air, gravity being the major one, and then air resistance. And depending on the environment, it's negligible. But for our purposes, we're going to go ahead and cross out air resistance, and we'll only look at the effect of gravity and the equations that we talk about. But a key component for projectile motion is to understand that the path of travel for projectiles is a parabolic path. And so the idea is that it goes up and comes down, and what goes up must come down due to the effect of gravity. And some of the stuff we'll talk about is if we know certain concepts as the way something leaves the ground, what can we then determine about how it returns to the ground? And there's a couple of ways that we will talk about to determine this motion and the path of travel. But one of the things I want you to focus on too is there are two components to a parabolic motion in the projectile motion. There's the horizontal and the vertical component, and we will teach you how to differentiate between the two and what equations to use. But where does projectile motion come into effect? And oftentimes when we're shooting a basketball, playing different sports, throwing a football, long jump versus high jump, jumping off a cliff, these are all different components of what's happening. And there are a few different components and determine how far we throw something or how far it's hit. But these are all key aspects of parabolic motion and how they apply to sport. A common area where you'll see the equations of uniform acceleration utilized, and those are the equations for projectile motion, is in, say, a home run derby or in baseball in general, when they can predict how far a ball has traveled and the path of travel. And oftentimes they'll take the takeoff velocity and the angle of projection, and they'll predict and calculate and transfer that out, as well as where the ball falls. But these are a common area. And then another area that we often see learn is when you're jumping off of a cliff. So you become a projectile motion at the moment here, and so determining how your path is. This is a common exposure where you take off higher than you fall. So one of the things we could utilize here is creating this double half parabolas and determining the velocity of entry into the water based off the velocity of takeoff. And we'll talk a little bit about how that works going forward. But sports and in human motion, projectile motion, and these equations that you will become familiar with are commonly used. But there are some key factors that will affect that parabolic path of projectile motion. One is that initial velocity. And what you'll see here is you're going to see the velocity represented as this blue vector, now becoming a red vector. And what that vector is that velocity. And as you look back and think back to one of the original PowerPoints of this class, when we talked about breaking it down to that original vector to its XY components, this is one thing that you'll have to do, because a portion of that velocity vector is in the vertical and the other portion of that is in the horizontal. And each one of those independently affect the projectile motion and parabolic path differently. But that initial velocity is the key component, especially how much vertical velocity you have going. And the second one is that projection angle, because what this projection angle is identifying is how much or what the percentage or effect of that vertical velocity or that initial velocity is in the vertical versus the horizontal, based off the laws of cosine and law of sine. And the final one, and the third one, is that projection height. How high from the landing surface it's taking off, or from the initial surface. So a basketball player is taking off the height of the ball is wherever the release is to the ground if we're tracking the ball to the ground. If the basketball rim is here, then the projection height may be that flat line across. So wherever the projection height is also determines it, because what that ends up doing is sometimes we'll have a parabolic path where the takeoff height is the same as the landing height. Other times we'll have it where the takeoff height is higher, or we'll have it where it's lower. So this determines how we break down these parabolas, or the halves of the parabolas, into our calculations. So when we if I ask you in class, what are the three major variables that affect that parabolic path or the projectile motion parabola, you would say the projection velocity, the projection angle, and the projection height, or that initial takeoff velocity, that initial takeoff angle, and the initial takeoff height. But understanding that the way that we leave, which are these three components, determine how we're going to interact and land with because of our equations of motion. So these equations are considered constantly accelerated motion. And we're going to talk about a few of them. And the idea of this constant acceleration is because we've already talked about the force that we're looking at is gravity. And because we live here on Earth, we know that our acceleration due to gravity is negative 9.81 meters per second squared. That is a constant. This does not change. So once something is in the air, it changes at a constant rate of acceleration, and that is negative 9.81 meters per second. So that is very important for us to go forward, and that is why they are determined and called equations of constantly accelerated motion. Now, there are going to be three of them that we're going to talk about in the vertical. These different individual variables, if we look at this, VF is the velocity just prior, and F stands for final. This determines the velocity just prior to it landing and hitting the ground again, to where it is no longer a projectile motion. So it's that final velocity as a projectile. VI is the moment it becomes a projectile. So this is velocity initial. Okay, so the moment it leaves the hand, the ground, whatever is using projectile motion. So whatever it's using to project it into the air. The A stands for acceleration. The T, now there's two different T's that you'll see. The small t is the time of half of the parabola. So we call it time up or time down. So you'll often hear this as, see it as small t with up or small t down, and then you'll understand that in a second. There's also going to be a big T here in a second that's not used in the vertical, but that is total time, how long it's in projectile motion. Okay. Now the D, sometimes you'll see it seen as an S, or you'll see it as a P, but that's the distance. So the height. In this instant, it's H for height. So how high from the takeoff to the apex. So, and oftentimes you'll see that D as an H, but so the very important part is these are the vertical components of the projectile motion, okay? If we go forward, here's that big T. So if we look at the horizontal, that is from takeoff to land, if I have my parabola, okay, and I go this way now, so this is half of my parabola. The small t is how long it takes to go from the takeoff, point A, to point B. So there's a time it takes to get to the apex, right? So B is at the apex. There's also a small t for the time it takes to get from B to C. Now, the big T is adding up these two T's. So the total time it's in the air. So now if the parabola takes off and lands at the same height or the same location in the vertical, then the two T's should be the same. So then the big T would be 2T. But very rarely does that happen, and sometimes one of the T's will be greater. So the big T equals the sum of T up plus t down. So an easy way to do this is just to calculate time up, calculate time down, add them together, and that's your total time. If we look at the last equation, our last variable, the VH, that is the initial velocity of the horizontal. So if we go back to that initial velocity vector, we break it up into its two components, and the two components are the law and cosine and sine. And here we have the VH. So whatever this velocity component is, that is going to be your VH, your initial velocity in the horizontal. So now I want to give you kind of a little exposure to how these problems would work and what you would want to, how you want to set them up. And there's an order of operations that I think would be really key of how you break things down, okay? So initially, what we would be given is a couple different things. I could give you, say the initial velocity is 25 meters per second, and the angle of takeoff was at 30 degrees. Or I could give you the initial vertical velocity was 25 meters per second, and the object was in the going upwards, or the time up was, say, 5 seconds. Okay. So then, then what we would say is this. Now you have to draw both of these out and see what they are. Okay. So this one, I would say, here's my velocity, original velocity vector at 30 degrees, and it's 25 meters per second. What this one tells me is that the vertical component is 25 meters per second, and that it was in the air for 5 seconds. Okay. Now, I will tell you right now, these probably don't match up. I just made these numbers up, so we'll see if it works. So what will happen is if I go forward with this information. So now after you've established what the word problem is asking you to do and you set up that initial diagram, this next step is going to be essential for you to understand what variables you know and what variables you need to find out. And so what I always do is I create up in the upper left-hand corner, and I want you to do this. If I ask you to do a projectile motion and you do not utilize this up in the upper left-hand corner, you will be docked off points, because this allows me to know that you are considering the true components and everything you need. And this is an order of operations for us. So what I've done up here is create each of the variables: initial vertical velocity, final vertical velocity, initial horizontal velocity, time up, time down, the acceleration, the distance or the height of the apex. In this one, you could also do D up and D down. I'll add that, D down. The range is the horizontal distance, and the total time in the air. Now, with this, understand that there are two initial vertical velocities and final. There's one up and down. So I typically will put a little line here so I can separate, and this is the time up. And you can do this also with all the other ones, just put them here if you want. So the way you create this is your ability, and you can do however you want. But I want to see all these variables in the upper corner. But how does this work, and how do we see this going forward? Well, if from the last page we saw that we had an initial takeoff velocity of 25 meters per second at a 30-degree angle. So what do we need to do? Well, we need to solve for VH and VI. So VI and VH, right? So VH is the initial velocity in the horizontal. VI is the initial velocity in the vertical. So VI we solve as 25 sine of 30, because it's opposite over hypotenuse. And then VH we solve as 25 cosine of 30, because it's adjacent over hypotenuse. These values now become your VIs. So what I want you to do on your paper typically, and I do this myself because I don't want to use it, I cross out all the initial information we no longer need, okay? And then now we're going to calculate all these individual, and the horizontal becomes 21.7 meters per second. And here we have 12.5. And this makes sense that for this the horizontal has a greater velocity because of the angle of takeoff. So now what I'm going to do is I'm going to come over to my diagram or information over here and input the information I know. So I know this is 12.5 meters per second. I know the acceleration, which is the negative 9.81 meters per second squared because it's gravity. And now we know VH, which is 21.7 meters per second. So as I go through this process and I calculate each individual thing, then I know this. Now, one thing you do know too. So if I told you that the initial height was the same as the final height, think about what you know about the initial velocity, the final velocity. If the parabolas are equal, the velocity, initial vertical velocity at takeoff, the final velocity right before landing is maybe equal and opposite. So I know that negative 12.5 meters per second is my final velocity because it's equal and opposite. Okay, that's just something you can know. Now what you have to do is utilize all those equations and put in the information that you have and don't have to figure everything out. So I can calculate now the time up, the time down. I can calculate final velocity. I can calculate the apex, the distance of the apex, everything based on going forward. Now this is what it's going to look like to go forward and solve. On the upper corner here, we have what we would use as far as our equations. And so you'll see each of the variables here. You know what variables you have. And so now what you're going to path is, and for this one, we're just going to say that it's an equal up and equal down because we have that with our velocity. And so what we're going to do is break the parabola into half. So all of the vertical components in all of these three equations here, the uniform accelerated, only deal with half of the parabola. And that's why it's a small t again. So we're going to calculate for time up. Okay, so what we have is we know the initial vertical velocity, we know the acceleration, okay, and we don't have any other information. Although what we do know also know the final velocity. And what do you think the final velocity is? Vertical velocity. Well, that's going to be 0 meters per second. Okay. And so what that makes is the initial vertical velocity for the other one is also 0 meters per second. And that's because at the top of this horizontal or the top of the parabola, that velocity has to be vertical 0 because it has to come back down. At some point it's 0. Okay, so that's what we do know. So now, if you look at the equations and find out what you know and what you don't know, there are two different ways you can go about this. Okay, so what we do know is that we have, yes, we know V final. Yes, we know V initial. Yes, we know A. So I could use that first one and solve for the time up. We also know here V final, V initial. We know that's a constant. We know A, so we can solve for D. I like to go the easier route, so I stay away from the squares as much as possible. So I'll solve for the T. And so now basically you're just going to plug and chug along the way. The V final going up is 0. V initial is 12.5 plus, and you just solve that for T. So you would come up with T up equals blah, blah, blah. And in this case, everything's going to be the same. So your T up is going to be the same as your T down, right? And so your total T will just be adding T and T. Because no matter what, if I change these variables around and put negative 12.5 over here, because if I follow this through, the 12.5 is subtracted, it becomes a negative on the other side anyways, and we just divide it by negative 9.81 and we get our T. Okay, so this is how everything goes throughout the line. So now you just plug and chug. You identify each component, you start plugging it in, and then you identify what variable over here you need to find out next. We'll use some examples of this, but if you have any questions, please let me know. This part here is just basic algebra, identifying what variable you have and plugging in. Remember to treat these as individual parabolas, because if I have these type of parabolas, then my VI here does not equal my VF here, right? All I do know for this situation is that my VF here is my VI. So now I have a different V final than I did a V initial. So understand that that's where this comes into play, why I would utilize these and only calculate half. This incident, it worked out where everything's the same, but if it doesn't, then we have to do it that way.